All right, everyone. Good morning. 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 It's kind of a cracking morning. I don't know, my two-story farmhouse. I didn't get much sleep. We're trying to sleep with all that rain and thunderstorm. It's loud. It's really loud. So it's kind of tiring in the morning. Let's see. Final quiz question. I got the quiz laying here. You got final question on this? Yes. 11. All right, 11. On 11. Okay, on 11, you got to melt this pig. So on 11, you got to melt this thing. So first of all, then you have a 10-kilogram block. If you want, I don't know, you know that that's 10,000 grams. I don't know if you want to do it in grams. We'll find out. It has an initial temperature of 30. So I'm going to write some things down. I know my mass. Now here's what I'm going to do. I'm going to take a look. And this is going to have to be given to you on the test as well. So this gives me my specific heat of aluminum. It gives me my enthalpy of fusion, and it gives me my melting point. But notice this is in grams. This is in grams. So I'm going to write down my mass, not in kilograms. I'm going to write it down in grams. So my mass is 10,000 grams. The initial temperature is 30 degrees Celsius. We're going to melt this thing. Well, we can't melt it until you get the temperature to its melting point, right? So there is two things we have to do here. We need to get aluminum solid from 30 degrees Celsius to 660, right? That's the very first thing you have to do. Now, what's the formula for that going to be? Q is equal to MC delta T. Once you get it to 660, you still have to melt it. What is that going to be? You're really going to take aluminum solid to aluminum liquid at 660. It's not going to change. What is that formula going to be? Q is equal to mass times the enthalpy of fusion. So you have to do two calculations here. So T final here ends up being 660. And you got your specific heat up there. So let's lay this first one out. So we know we're going to use for the first part, Q is equal to MC delta T. And I'm only doing this because I want to write in the units, because I want to change some of you guys' ways. I see just numbers, especially when I correct labs, I want to cry. There's just numbers with no units at all. None. So if you write down your units here, like this for sure is 10,000 grams. My specific heat is 0.215. Zoom this out a little bit here. Is 0.215 calories per gram degrees Celsius. And my temperature change is 660 minus 30. And once I write this down, I should be able to do this. Grams cancel out with grams. Degrees Celsius are all going to cancel out. My final answer there is going to be in calories. So if you write your units down, it sure does make life easier to know you have the correct units. So this is your first calculation, but you also have to calculate your mass here times your enthalpy of fusion to finish this. So, and then add them up, right? Because there's two things you have to do. All right, any other questions on this quiz? Yes.
16.
16, let's see. All right, so 16, I've got it highlighted. And if we take what we have highlighted in pink, and what I did, I think I did it, I don't know, I would have it like this on the test, and I think I've got, it'll look something like this, delta H equals question mark for this one, because this is what we're looking for, right? And then I'm giving you 2 or 3 equations like this. So we know that we have 2 carbon monoxides on the reactant side for the one that we're looking for, but here's carbon monoxide on the product side. So we know for sure that we are going to take this one, and we're going to have to reverse it. And what else? Yeah, we're going to have to go reverse times 2. And what are we going to have to do with this one? I mean, the CO2 is already on the product side, but there's a 2 there, so it looks like we can just kind of multiply that one by 2. It should fall out, I believe. That'll get my numbers correct. And you're going to have oxygen on both sides. All right, anything else on this thing? All right, we're going to retire this. When you get to the quiz now, there are learning guide questions that should match up almost exactly to these when we did Hess's Law. What page? All right, we're going to retire this baby. So this is due tonight at midnight. And one of my students, well, this is 11:55. I think Canvas used to be 11:59. And I think it was 59 seconds, as they told me yesterday in my class. And it's 59 seconds. I need a 59 seconds. Canvas, I think nationwide did an update this past semester, and I think it changed to 11:55, and I just rolled it. I didn't go back. I think it now defaults instead of 11:59 to 11:55. Anybody verify that? Is the time on the due, is it 11:55 or 11:59?
It depends on the stocks.
It does, so it does change.
Yeah.
So it's either 11:55 tonight or 11:59. Yes. 11:59? Okay, let's look at this. Now, if you printed this out or if you have this, this is chapter 6 and 7 together. And I'm going to be paging back and forth. We're going to skip today right into chapter 7 because that makes the most sense to explain it. So we're going to do a little bit here. You're going to see me skip way forward and come back. It's just needs to be explained in a much different order than what the book presents it. But here's what we talked about last time. We know that C is equal to lambda times the frequency. Now, this is the speed of light. We are going to round this. When you do the problems, just round this to 3 times 10 to the 8 meters per second. This is wavelength. And that wavelength should be in meters then. And this F should be frequency. Now, for frequency, you're going to see this unit. It is actually hertz, but what is a hertz? S to the -1. It's 1 over seconds. So make sure these are the units you have. So you're going to use C is equal to lambda F a lot. We're going to do it on this first page. Now, then what we looked at is we looked at the electromagnetic spectrum. I had to print this at the college. I got a new yellow cartridge at home and it's plugged. I still don't have yellow at home. Then we looked at this. And just this fact right here, this arrow here, as you follow this, is like, I don't know how many owl questions. If we look at these waves and I turn them like this, it's a better orientation. Last time I said sound, if you turn your volume up, your speakers are sucking in more, releasing more. Higher amplitude would just make the wave higher. Otherwise, we have wavelength, the distance from crest to crest, trough to trough, something bottom to top. And then you have how many waves per second. And as we go to the right, as you see this, which is your right, yes, you get more waves getting closer and closer together. As we go this way, we get a higher frequency. But as you get a higher frequency, you get a shorter wavelength as you go, right? Now, this frequency goes with energy. Obviously, you're not listening to your radio and getting your skin burned, right? Radio waves don't burn your skin. What burns your skin? Ultraviolet, right? UV rays are going to burn your skin. So you can go over here and over here. So that makes sense. Those rays start breaking down your skin cells and they are wicked. And you get over here, x-rays aren't good for you and gamma rays aren't good for you, but ultraviolet is what's going to affect your skin. Now, you see color with this as we go this way. Way back, they looked at pottery was a big thing, right? But that's a big major discovery, is that you could actually fire pottery and you could start hauling stuff around, right? Otherwise, you hauled it in a skin. Everything was about furs and skins, and the fur trading was big, and then spices. But pottery turned out to be a big thing. Well, early on, they thought they could see something glowing red hot. Well, what if the pot was glowing yellow? Is that better? Well, they did figure out it works the same thing with glowing pottery. The further you go up this way in color, a blue flame is going to be higher energy than a red flame, where the bottom of the pot's burning red isn't going to be as hot. So they found that color and heat go together. So then also in color, we are going to explain today probably is we see something that is on page 11. And early on, they are seeing these different colors when looking at hydrogen gas through a prism or something that can separate the light, and they're trying to explain that. Now, let's go back to the first page, because we're going to come back to this. Here's my example. Let's pretend the speed of light, instead of 3 times 10 to the 8 meters per second, is 24 meters per second. So if the speed of light is 24, you cannot change the speed of light, right? That you're not going to change that. You don't have any control over that. What you have control over is your frequency and your wavelength. Well, what if your wavelength is 2, and we know that C is equal to wavelength times frequency? What's my frequency here? 12, right? If your wavelength increases, what's your frequency going to do? It's going to go down to 3 in this case, right? Wavelength goes up, frequency goes down. What if your frequency goes up? What if it goes from 3 to 6? Then your wavelength goes down to 4, right? These are opposites of each other. If your frequency goes up to 24, your wavelength, you better have those waves closer together. Your wavelength's going down to 1. And if your wavelength gets cut even more, your frequency is going to be at 48. Right? Again, they have to work opposite. So if we go back to the same diagram, wavelength decreases this way, going this way, we know that frequency and energy, right? Frequency and energy, remember, they go together. Frequency and energy increase. Wavelength increase is going down. Okay, so here's an example you can maybe relate to. So we should be about right here. To give you an idea of the difference in wave characteristics, you may listen to 92.9 DX. Anybody in here? Are you kidding me? Not one person listens to 92.9? Benny, you do? Okay. For an FM station or 790 kilohertz. Now notice this is megahertz. Mega here and kilohertz here. I'm not even going to ask you if you listen to 790. I'm going to assume you do not. For an AM station, if you use 4G cell signals at 700 megahertz, you may use that. The FM on your FM dial stands for frequency modulation. Again, that is in megahertz on FM. The AM stands for amplitude modulation. The frequency of hertz of 92.9 then is 92.9 times 10 to the 6th. This is my mega, right? And the frequency in hertz of 790 is 790 times 10 to the 3rd, because this right here is my kilohertz. Let me put in my megahertz up here. Those are frequencies. Therefore, the wavelength of 92.9 FM wave is blank meters or blank feet. Now, let me ask you a question. Can you listen to a station at a farther distance on AM or FM? AM by far. But AM interferes if there's an electric fence or on the farm, it will beep at you. If you go over a metal covered bridge, you will lose your signal in and out. But AM by far, especially on a clear night, you can listen to AM. You can get Chicago from here, and AM will travel farther. So we're going to calculate this out. We want the wavelength in meters and feet of 92.9 FM. What guys listen to? Z100? How many listen to country? Some do. I can listen to country so long, and then I just got to change it because write a country song, right? Got my girlfriend in the pickup truck, dog jumped in, licked her face, got a beard, rode down to the river. There's my country song, right? I got girlfriend, pickup truck, dog, river, I got water. We can go fishing, right? Okay. So here's what we got. We're doing C is equal to lambda F. Yeah, let's identify everything here. We gotta figure out wavelength here. So let's just solve this for the wavelength right away. So we've got, well, C divided by frequency is going to be my wavelength. So let's plug this in. So this is going to be 3 times 10 to the 8th meters per second. Divided by my frequency, I'm doing 92.9. .9 times 10 to the 6th, but it's a mega. In this, I'm going to write it like this. It's seconds to the -1, or 1 over seconds is the same thing. That's frequency. It's 1 over seconds. And I do this because I'm showing you that this unit and this unit should cancel out. So grab your calculator, punch this pig in. I get 3.23 meters on it, right? Okay. So we get 3.23 meters. And I want this in feet as well. 1 meter, 3.281 feet. So this is 3.23 meters. And how many feet do I get out of this? 10.6. 10.6 feet. Uh, 10.6 feet. Now let's do the same thing for FM or AM. I'm sorry, AM. Oh, by the way, your FM dial, way on the left of your dial. Crap, nobody has a dial anymore. What am I talking about? Yeah, nobody does a dial. You push button. I don't know. The bottom on FM is what? Get down to about 88, huh? 87, 86, up to almost 108, right? On AM, you have any idea? You get about 530 up to 1500, I think. 790, do the same thing. We're just gonna go 3 times 10 to the 8 meters per second divided by 790 times 10 to the 3rd hertz. Oh, and then I put hertz in this time. I don't know why I did that, but 1 over seconds, that's going to cancel out. I am going to get 379.7 meters, I believe. And then if I convert that to feet, 1 meter, 3.281 feet. I get 1,246 feet, I believe. Almost a quarter mile. So here I've got, let's fill this in, 379.7 meters, or 1,246 feet. That is a long wavelength for AM. 10 feet versus 1,246 feet, that's almost a quarter mile. So let's go to our chart. And where I have radio waves here now. The longest wavelength to the left is going to be AM. So let's put AM here, and let's put FM. I guess I should. Yeah, AM then FM, right? Would make sense on the chart. Okay, let's do the bottom calculation. I think this is very, very similar to OWL, but we'll do an OWL question coming up here, I believe. Cell phones cover range from 800 megahertz to 2 gigahertz. So mega times 10 to the 6, giga times 10 to the 9. What is wavelength in meters of a cell phone signal operating at 1.12 gigahertz? So the wavelength. So here's what we know. The speed of light is 3 times 10 to the 8 meters per second. My frequency is 1.12 times 10 to the 9th hertz, or 1 over seconds, or seconds to the -1. And my speed divided by my frequency again is wavelength, and I should be able to plug this in. You notice I should end up with a wavelength in meters, right? And I get 0.268 meters. Okay. Let's go to the next page. So we say that electromagnetic radiation or light is composed of two orthogonal vectors. An electric wave and a magnetic wave. Here is the amplitude that I've talked about, right? It's the height of the wave. Then we've got wavelength from crest to crest. And we have frequency there. You see this in two different planes. They call it a magnetic vector and an electric vector. So electromagnetic radiation consists of oscillating electric and magnetic fields traveling through space. All forms of electromagnetic radiation travel at the same rate, which is equal to the speed of light in a vacuum, 3 × 10⁸ meters per second. You will see electromagnetic radiation described as both a wave and a particle, photons. No single experiment has yet been done to show electromagnetic radiation behaving simultaneously as a wave and a particle. Scientists now accept this wave-particle duality. That is the idea that the electromagnetic radiation has the properties of both a wave and a particle. Probably take an entire semester class on that if you wanted to, but it's way beyond what I want to talk about in this class. Let's go to this page. All right, again, this should be reviewed. The higher the frequency, the lower the wavelength, the higher the energy of the wave. Think of visible light, Roy G. Biv, but they took away indigo. You won't see this. I had to search for a long time to find this thing. Because they say that people cannot distinguish the color of indigo versus blue. They got rid of indigo. Just like they got rid of Pluto, huh? How dare they do that after all these years? So, Roy G. Biv, orange, yellow, green, blue, indigo, violet, in which red light will have a wavelength of, up here, 700 × 10⁻⁹ meters, and a frequency of 4.28 × 10⁻⁴ hertz if we calculated that out. And that would be terahertz. And violet light will have a wavelength of 400 × 10⁻⁹ meters and a frequency of 7.5 × 10⁻⁴ hertz. Which one has a higher frequency? Well, 7.5, right? 7.5 is bigger than 4.28. So we know, therefore, the higher energy light is the one that has the higher frequency, and that light has to be violet. And this is a quick owl question again, but here we got to calculate frequency. And if we're going to solve this for the frequency, so 3 × 10⁸ meters per second divided by 600 nanometers. Now grab your calculator, make sure you're putting this in your calculator correctly. Grab your calculator. Everybody's having a winner day when they have their calculator going. Grab your calculator, be a winner today. Grab your calculator, punch this in. So we get, what we get 5 times 10 to the 14th. Right. Five times 10 to the 14th. Well, that's, this is the beginning of chapter 6. We're now going to go to chapter 7, come back. This page right here is just a diagram again. It just puts it in this perspective. It breaks down visible light maybe a little bit more. This down here does wavelength, frequency, and photon energy. We'll talk about photon energy later. But to explain all this in chapter 6, they're talking about what the electron does. So they're talking about the electron moving from energy levels, but they really haven't talked about, explained anything about energy levels yet. So I want to go to top page 13. At one time in your existence, you've probably seen a diagram like that that has the nucleus in these things that look like orbits. Everybody's seen something like this, okay? So I want to also reiterate that this is not drawn to scale. If they're going to make the nucleus that size, this ring that you see up on your screen right now would go clear to Water Street probably. This is way, way not anywhere near scale. The electron cloud, where the electrons are traveling around the nucleus, is just a tremendous amount of space. Then you probably at one time said, well, closest to the nucleus, we can only put 2 electrons. Does that sound right? Somewhere like that, you can put 2 electrons closer to the nucleus. Then you got to go farther out, and then farther out, we can put 8 electrons and so on. Does that sound familiar? I'm sure it does. We got 7. I got to stick another one here somewhere. So what does this N stand for? Energy level. So we know that the electrons are going to want to stay close to the positive pole of the nucleus, but they have the same negative charge. They're going to repel each other. So how many can we put close to the nucleus before they repel each other and we can't do it anymore? Well, in the first area is only 2 electrons. Then we got to go farther out and farther out. Now this looks like the orbits of the planets. This is not how it goes. This is in 3-dimensional space. So this is my summary. The shells of atoms can be thought of as concentric circles radiating out from the nucleus. Think of the following spheres overlap on each other. You take a regular BB, you put the BB inside of a marble, you put the BB and marble inside of a ping pong ball, you put the BB marble ping pong ball inside of a tennis ball, you put that into a softball, into a soccer ball, into a beach ball. If you add up all of these together, you will have a total of 7 shells, right? They just get bigger and bigger and bigger, but the smaller ones are inside the bigger ones as you go. The higher the energy level, the more energy the electron has. So if the electron is way, way out in energy level 3, it has more energy than if it's in energy level 1. This is no different than gravity. If you throw something up higher, it's going to come down and hit you in the head if you're not careful with more force, right? Obviously, if you just throw it up a little bit, it's not going to hurt as much. But an atomic orbital, which is distinct from an orbit, oops, I skipped. You can think of these shells as energy levels, and they can be specified with the letter N. Again, 7 energy levels. The higher the energy level, the more energy the electron has. So We are talking about electrons. And we're going to talk about electrons being boosted farther away from the nucleus. Now let's just talk about the electrons involved in this room right now, mostly in the form of light. These lights. That is caused by electrons. Where are the electrons coming from? I could suggest to you that they're perhaps, this is XL energy, they could be coming from the Prairie Island Nuclear Power Plant in Red Wing, Minnesota. Perhaps, I don't know for sure. But we do know this. If I take a copper wire, do not write this down at this point. We're going to talk about this again. If I have copper, it turns out that the electrons surrounding the copper, these electrons do not care what copper they're around. Well, let me ask you a question. If I unrolled a water hose all the way to Red Wing, Minnesota, I unroll the water hose all the way to Red Wing, Minnesota, and it's full of water. If I turn the spigot on in Red Wing, Minnesota, hold my water hose up here, am I going to pretty much instantly get water out on my end? Yeah, absolutely. Did that water instantaneously come from Red Wing, Minnesota to me? No. When you flip a light switch on, it is the same exact thing. You get electrons to go through your lights. Did they instantaneously come from Red Wing, Minnesota? No, they are getting pushed along. So from Red Wing, Minnesota, they're pushing and adding electrons in, and that electron goes from this carbon to this carbon to this carbon, or carbon copper. Just like you have a flow of electrons down the wire, you have a flow of water down your water hose. Voltage is just a push of electrons. Think of voltage. If you've got a 75,000 volt power line, think of that as a water tower. You put a bigger water tower up higher, you're going to be able to push more water. The higher the voltage, the more push of electrons. So we are just talking about the flow of electrons where we're talking about electricity. Once the electrons get here, though, we do something to them, and that is we kick these electrons out farther away from the nucleus, and they come back down and give the light back. So the electricity needs to kick the electron out. The electron falls back down, and they give us energy back that they absorbed in the form of light. Now, LED lights are a big game changer. Originally, it was a piece of metal in there. What was that piece of metal? What did Thomas Edison use to make electric lights? What did Thomas Edison use? Tungsten. And really what that tungsten light is, it's glowing in there, orangish hot, orangish white hot. And you're wasting energy, right? They get really, the old screw-in light bulbs, they would burn your fingers, correct? Everybody, I think, is old enough yet to maybe have messed with the old incandescent light bulbs. But once the electrons get here through the electrical wire, especially if you have fluorescent tube lights, there is no tungsten filament in there. The electricity in the gas tube of the old fluorescent lights, and everybody knows what that is, the electron gets boosted out by electricity, it comes back down and gets its energy in the form of light. Now, what the scientists were looking at, and they didn't know it, was you actually, and this is what we have to explain, is this. And Balmer was able to figure this out. If that electron that we've zapped farther out from the nucleus, it is in energy level 6. If it drops back down to energy level 2, that's going to give us this color light. If it's in energy, it gets boosted out to energy level 5 here, comes back down to energy level 2, we get this colored light. Energy level 4 down to energy level 2, we get green, and energy level 3 down to energy level 2, we get red. So the early scientists trying to say, how the heck do we get these colors? They don't know what's going on at all. At all. Nobody knows what's going on yet. But eventually we figure out this is what's happening. This is where we get visible light. Let me say this again. This is where we get visible light. Where do the electrons have to drop back down to? What level in my diagram? They drop back down to energy level 2. Energy level 2. This is visible light. So when the electron gets boosted out farther away from the nucleus, comes back down to energy level 2, that's visible light. If it gets boosted out, comes back down to energy level 3, this is infrared. And this is UV over here if it goes to energy level 1. So if you can just control that electron, keep it going down to energy level 2. If it goes down to energy level 1, you get UV. So we've got a lot to figure out here. We've got to figure out where the electrons go, how many electrons, how much energy the electron has, how much energy and what wavelength do we get dropping back down and stuff. So you'll see lots of pages. Benny.
Are we ever going to be using units like candelas?
Like units of what?
There's
Candela? Did you say candela?
yep, candela.
No, we don't use that. No. Okay, so going forward, there's a lot to explain. I've got it dialed in pretty good. We're going to skip around in these pages. Next time, we're doing electron configuration notation. Explain where the electrons are. We're going to explain some of these orbitals. So, in diagrams that look like this. To study for the exam, make sure to go through your quiz questions after you go through the quiz questions. The learning guides have great example problems in them. I would do the quiz questions followed by the learning guide example problems followed by OWL. Okay, I will be here a little bit early Friday. So if you have time to get started a little bit, there's only 20 questions, 10 from each chapter.